Hi, everybody. So that good morning or good afternoon for somebody who is watching this from other countries. I'm happy to present the first speaker of the today's section, Professor Edson Sampaio. He's a mathematician, young but already quite established, and he is working in Lipschitz geometry of singularities and some question related to the Zariski multiplicity conjecture. So today he's going to talk about these things, about the things related to the multiplicity conjecture. And actually, I would like to say, just from my own, let's say from my own name, that actually the significant progress of the just in the Zariski multiplicity conjecture today is actually quite related with his name. So that starting from from his thesis and up to now, he makes just very significant works in the Zariski multiplicity conjecture. So that I'm very happy just to present him as a first speaker of the today's session. Thank you.
So, thank you, Lev, for the introduction. I would like also to thank the scientific and the organized committees for inviting me to participate in this event. So, I want to say some initial considerations. The first one is the results here. Oh, sorry, I have a problem. So the results here are in the preprint on characterization of smoothness of complex analytic sets, which is a joint work with Alexandre Fernandes. You can find this preprint in my ResearchGate webpage. You just can write this address, or you can put my name in ResearchGate, and you can find just that preprint. Okay, so let me state the Mumford theorem here. Mumford proved in 1961 the following theorem: let X be a normal complex surface at the origin if the link at zero of X, denoted here L0X, is simple connected, then X is smooth at zero. So in particular, if the link is diffeomorph to a three-dimensional sphere, then X is smooth at zero. Let me remark that the Mumford theorem gave a partial answer for the Poincaré conjecture, which is a theorem nowadays. In the case of a three-dimensional compact manifold M, which is diffeomorph to the link at zero of a normal complex surface X. It's clear, no? It's just a remark. So let me say the theorem of Mumford is not true in higher dimension. This was proved by Briscorn in 66, so 1966. He presented this following set, which is not smooth at zero, but its link is diffeomorph to S5, this five-dimensional sphere. So, okay, so we don't have a positive answer to Mumford theorem in higher dimension, but when we have a set when you can put some hypothesis to obtain the set is smooth. In other words, we have natural question. I have, for example, let X be a k-dimensional complex analytic set with 0 in X. So the first question, when X is smooth? A second question, a weaker question, assuming that the link is diffeomorph to a sphere, when X is smooth at 0. So we have some answers to these questions, and let me present some of them here. For instance, Priel proved in 1967 the following. Let X be a k-dimensional complex homogeneous algebraic set if its link at 0 is 2k minus 2 connected, then X is a linear subspace of Cn. And in particular, its link at 0 is isometric to the 2k minus 1 dimensional sphere. This, in fact, is a Bemstein-type theorem. You can see this. You obtain a result that you put some hypothesis and obtain the set is a linear subspace. This kind of result we call Bemstein theorem, Bemstein-type theorem. So a second answer was gave by Acampo and Le separately. In fact, they proved that if X is a complex hypersurface, which is a topological submanifold of Cn, then X is smooth. So more recently, we have also some answers from, for example, from the contact geometry point of view. We have the theorem proved by MacLean in 2016. He proved it for a three-dimensional complex analytic set with a normal isolated singularity at 0. Its link at 0 is contact diffeomorph to the 5-dimensional sphere. If this happens, then X is smooth. In fact, if and only if. This, the converse is also true. So, in fact, we have a conjecture. This was conjectured by the Phoenix and Tu. In fact, they also gave some answers to our questions in that paper, in the paper 7. In fact, they conjectured the MacLean theorem is true in n dimension. In other words, they conjectured a set is smooth at 0 if and only if its link is contact diffeomorph to the 2k minus 1 dimensional sphere. If the canonical structures on the link and on the sphere, of course. So another theorem, also recent, another answer was from the Lipschitz geometry point of view was given by Bibraí, Fernandes, Le, and myself in 2016 also. We proved it for a complex k-dimensional complex analytic set. If that set is subanalytically by Lipschitz homeomorph to some Euclidean space with the same dimension, then X is smooth at 0. So, in fact, after that, I removed that subanalytic hypothesis in the paper 9. I obtained the same result. If X is by Lipschitz homeomorph to some Euclidean space, so X is smooth at 0. And more recently, using moderately discontinuous homology, a homology theory developed by Fernandes Bobadilla, Maria Pereira, and Sonia Hens and myself. With that theory, we proved the following. If X has the same moderately discontinuous homology of some Euclidean space, then X is also smooth at 0. So, in fact, this is the main answers that I want to present. So I want to state the theorem that I want to talk about. The main theorem here is the following. If X, let X be a complex analytic set with dimension K at 0 in X. If X is C LLNE at 0 and its link at 0 is simple connected, then the following conditions are mutually equivalent. The following one is X is homology to K manifold and locally linearly contractible at 0. X has no choking cycles at 0 and its link has homology group trivial in this interval. Okay. And third, the link of the tangent cone at 0 has also homology group trivial in this interval. And X, each one of these, before items are equivalent to X to be smooth at 0. I will define what means each one of the object I said here, LLNE, homology manifold, no tracking cycles, and now to for you understand the statement. Of course, if any of the above items hold true, we obtain, for example, the link is diffeomorph to a sphere. Okay? So let me say some preliminaries now. Given a path connected subset X in Rn, the inner distance on X is defined as follows. Given 2 points x1 and x2 in X, the inner distance of x1 and x2 is the infimum of the lengths of paths on X connecting x1 and x2. So the definition is the following. Let X be a subset. We say that X is Lipschitz normal embedded, shortly LNE, if there exists a constant C greater than 1, such that the inner distance is less than C times the Euclidean distance for all points x1 and x2 in X. In this case, we also say that X is CLNE, to put the information of C here also. So we say that X is LNE at P if there exists some open neighborhood U of P such that the intersection is LNE. To make sense a local definition now. So the definition of LLNE is the following. We say that X is LLNE at P, Lipschitz normal embedded, link Lipschitz normal embedded, if there exists some C and delta such that the set XT, defining the following, the intersection of these two sets, is CLNE for all T less than delta and greater than 0. In this case, we also say that X is CLLNE at P. Let us mention that in a progress paper, Rodrigo Mendes and I proved that these two notions, LNE and LLNE, are equivalent for subanalytic sets. Let me show some examples. If you take a subanalytic subset, and if there exists some subanalytic by Lipschitz homomorphism between X to some Euclidean space, then X is LLNE at 0. Another example is if you take n smooth submanifold in Rm, then it is LLNE in n point of X. Another example is n compact smooth submanifold is LNE. Another example is the following. If you take a complex analytic set with an isolated singularity at 0, then for the last example, xt, for example, is a compact and smooth submanifold, so is LNE by last example. So there exists some CT greater than 0, satisfying this inequality. So the set will be a LLNE just in the case this constant CT does not depend on T. This is an important example. So in fact, in the case of complex homogeneous algebraic set, homogeneous here are that set which are 0 set of homogeneous polynomials with isolated singularities LLNE. This is just because xt does not depend on T. Because this is, in fact, this is a cone. So the definition of tangent cone, it's important here. So we say that V in Rn is a tangent vector of a set X at P if there exists a sequence, sequences Tj of positive numbers and Xj in X, such that the limit of Tj is 0, and this another limit is V. This other limit is V. So we denote by CXP the set of all tangent vectors of X at P, and we call it the tangent cone of X at P. An important remark is if you have a complex analytic set, the tangent cone is a complex homogeneous algebraic set. The zero set of a set of complex homogeneous polynomials. So another important definition is the following. A metric space is said locally linearly contractible, LLC, if for every compact set K in the space, there exist numbers K, Rk and Ck greater than 0 and greater than 1, such that every metric ball Brx in the space with center X in radius R, less than Rk, contracts to a point inside of this ball centered in X with radius Ck times R. This is because this is called linearly because this is linear with respect to R. Okay. So a separable and metrizable space X is a homology n manifold with n greater than 2. If X is finite, homological dimensional, locally compact, and locally contractible, and the integral homology group satisfies the following identity. So locally is the local homology is the same of Rn, in another word. Okay. So we say that X is a LLC homology and manifold at P if there exists some open U of X at P of P such that neighborhood is a homology and manifold and LLC if locally satisfy both definitions. Another important definition is choking cycles. We say that a set has an n-dimensional family of choking cycles at 0 if there exists constants lambda greater than 1 and delta greater than 0, and there exists a family of n-dimensional integral singular cycles, QCT, such that each QCT is in the set XT, which is that intersection, and the limit of the diameter of QCT goes to 0 as t goes to 0. And C, if eta t is a family of n+1 dimensional integral singular chains such that each eta t is in xt, and the boundary of eta t is QCT for all t, then the limit of the diameter of eta t is greater than 0. So let me mention that the existence of choking cycles where QCT are spheres is an obstruction to the germ being bi-Lipschitz homeomorph to a cone. This was proved by Bibraí, Fernandes, Grandjean, Yoshia in the paper Choking Horns in Lipschitz Geometry of Complex Algebraic Sets with appendix by Walter Neumann. Important, I think I will not define what means multiplicity here. I think I will not have time. In fact, it's a well-known definition. So I will come back to the main result once again, but before I want to state an important result about rigidity of fundamental groups of LNE sets. This following theorem was proved in the same paper, so this is important alone. But this is a lemma in the paper, but it is, as I said, it's important alone. This is why I want to state it here. If let x0 and x1 be compact, there is a mistake here, a typo, there's no A. Compact subanalytic C LNE subsets. So let epsilon 0 of xi, the biggest real number, such that n loop on xi with length smaller than epsilon 0 is homotopically trivial. This number exists. So if the Hausdorff distance between x0 and x1 denoted by this way, is smaller than epsilon 0 over 20 times c squared, then there are a basic point x0 and x1 and an epimorphism from the fundamental group of x1 onto the fundamental group of x0. Moreover, if you take the distance satisfying this inequality, it's the same inequality for both epsilon 0, we can take this following epimorphism being an isomorphism. Let me give some examples. For example, this hypothesis is important, CLNE. As you can see in the following example, you can take this circle, deform it, but it's a topological circle, and you can take in such a way this is close enough to this wedge of two cycles, but we don't have any epimorphism from the fundamental group of this set onto the fundamental group of this set. This is a free group, free product group. This is Z. So you cannot obtain this. Another example in R3 is the following. You can take the following topological torus. This can obtain close enough to the wedge of two pinched torus, like the picture T0, and we also cannot obtain the following a epimorphism from the fundamental group of TT to the fundamental group to T0. Important consequence of the theorem is the following. If you have a subanalytic set, and we assume that set is LLNE at 0, so if the link of X is simple connected, then the link of the tangent cone is also simple connected. This is important for us, and I can explain why just now. Let me state once again the characterization of smoothness. If X is CLNE and its link is simple connected, now you know what means CLLNE at 0, and is simple connected. So the following statements are equivalent. So the first one is X is an LLC homology to K manifold at 0. So now you know what means each definition. Second one, X has no choking cycles at 0, and its link has trivial homology group in this interval. And the link of the tangent cone has trivial homology group also in this interval. But let me remark now, because I'm assuming X is CLLNE, and the link is simple connected by corollary, I obtain also the link of the tangent cone is trivial, is simple connected. So I obtain, for example, all the homotopy groups are trivial from 1 to 2k minus 2. This is important. This is important to prove the theorem. And of course, the fourth one is X is smooth at 0. I think I don't have time to prove. I thought I would have time to give some idea. But if you want to learn about the proof, you can read the paper. I will skip the idea of the proof because I want to state some applications of the theorem and also of its proof. So let me skip this. Sorry. Want to go to some applications. Let me state the following result of smoothness in a simplified way. If X is a complex analytic set, then X is smooth at 0, if and only if the fundamental group of the link is isomorphic to the fundamental group to the sphere of dimension K. X is LLNE at 0, and the homology group are trivial in this interval. Okay, oh, sorry. A second corollary that you can obtain is the following. If X is a complex analytic set which satisfies this triviality of the homology, in the homology of the link, and also we have the fundamental group of the link is 0. In other words, the link is simple connected, the link of the tangent cone. This is just, I'm assuming the hypothesis that I needed to use, in fact, I needed to use LLNE to obtain this condition. But if I assume this condition, I don't need the LLNE hypothesis to obtain, for example, the tangent cone is a linear subspace if I assume X is an LLC homology to K manifold, or has no choking cycles at 0. If X satisfy one of these two hypotheses, and also this hypothesis, so the tangent cone is LNE, and I don't need to assume X is LLNE at 0. This corollary is important to give an important counterexample. It was an expectation of some people that I talk that it was an expectation that X being a complex analytic set always was a LLC set. But in fact, that's not true. The following example says, give a counter example. For each K, we can consider X defined this way. In fact, this set was proved by Briscorn. Is a topological manifold. So in particular, its link is homeomorph to a sphere. So in fact, because it's a topological manifold, it is a homological manifold. And of course, because the dimension, we have the link of the tangent cone, the zero set of this part, is because this dimension is greater than or equal than 3, for example, the dimension of the tangent cone, because K, this is at least 4. So the link of the tangent cone is trivial. So because the corollary here, the last one, X is a homology to K manifold. This is also satisfied. This also is satisfied, but because the tangent cone is not a linear subspace, X cannot be LLC. Because the tangent cone is not a linear subspace, as you can see. The tangent cone is just the zero set of x1 square plus blah plus x2k minus 1 square equal to 0. So in the theorem, another remark, let me do some analysis on the hypothesis of the theorem. We cannot remove the condition that X is LLNE at 0. The following set gives counterexample. If you take the cylinder of the cusp, satisfy the following, the fundamental group is trivial of the link. The link is simple connected, and the homology satisfy this is trivial in this interval, in fact, only for I equal to 2. But X is not smooth at 0. This is why I cannot remove the condition X is LLNE at 0 in our theorem. More examples. We cannot also remove the condition on the link of the tangent cone, on the homology of the link of the tangent cone. As you can see, the following set is LLNE, this is a cone. The link is simple connected, but X is not smooth at 0. So this is why I cannot remove the condition on the tangent cone, because this set does not satisfy this condition. So this is why the set is not smooth. Okay, smooth. Another thing is the theorem does not hold true in the real case. as you can see in the next example, the homogeneous algebraic set X given by X1 2019, X2 2019 equal to X3 2019 in R4 is a semi-algebraic by Lipschitz homeomorph to R3. So we can prove, because that, we can prove X is LLNE at 0, is LLC, is a homology three-manifold, the link is simple connected, but as you can see easily, X is not smooth. So this is why we cannot remove, we cannot change the word complex by real in the theorem. So let me state the following corollary, assuming putting conditions on the sectional curvature. Let X be a complex analytic set with an isolated singularity at 0. So assume that the link is 2k minus 2 connected. For example, in particular, if X is a topological manifold, for example, and X is LLNE at 0. So if there exists some constant such that the sectional curvature of xt denoted by kxt satisfies this inequality for all small enough t, then X is smooth at 0. In particular, we obtain also a sphere theorem, right? You can obtain the link of X is diffeomorph to a sphere. This is a kind of, the last part is a kind of results called sphere theorem. You put some condition on the sectional curvature, on condition the geometry, and you obtain the set is, the manifold is diffeomorph to a sphere. This is also can see a theorem like that. Another important consequence is the following Bemstein-type theorem. In fact, we have the following. In fact, this we are looking at infinity now, so we can define what means LLNE at infinity, like we define locally. We define, for example, it's easy. You can intersect with a sphere or radius big enough, and look the inner distance, etc. So you can define the link at infinity of X in the same way. You can define what means choking cycles at infinity in an analogous way also. So if you come back to definition, think a little bit how to define that objects, what means LLNE at infinity, what means link at infinity, what means choking cycles at infinity, we can understand very well the following statement. So if you have a complex algebraic set which is LLNE at infinity, and you assume that the link at infinity is simple connected, so we have the following statements, equivalent statements. So, for example, X has no choking cycles at infinity, and if and has a trivial homology group. The link has trivial homology group in this interval. This is also equivalent. This is equivalent to the link of the tangent cone has trivial homology group in this interval. Also, we can define what means tangent cone at infinity, changing the sequence Tj going to 0 by the sequence Tj going to infinity, for example. and then you can obtain all the vectors, tangent vectors at infinity, like that, like we define locally. So the two first conditions are equivalent to the third one, which is ask that X is a affine linear subspace. This is because this is why we said this is a Bemstein-type theorem. We are putting some conditions on X, and we are obtaining that X is an affine linear subspace. Of course, each one of these conditions, because each of the first two conditions are equivalent to the third one, and the third one is easily equivalent to the following statement. For each P, this set is just the link at P, is isometric to the sphere for all T. If you have this, you obtain, in fact, X need to be a affine linear subspace. Of course, if X is a affine linear subspace, intersection with a sphere is a sphere centered in a point of that point. So this is what I want to talk. Thank you very much for your attention.
Hi. So, what about the questions? There were some questions by David Trotman, but actually, I think I answered him. But let me put them just publicly. For instance, that if you have a C1 submanifold, is it locally L and E? Right? If you have a C1 submanifold of R to the N, is it locally L and E?
C1 is not. Yes, of course, yeah. C1 is not.
Another question of David is that you, in your example where you had that X and Y and Z with the powers 2019, could you replace them by 2019 by 3?
Yeah, of course. I can replace for any odd number. If you
replace for any odd number, sure.
Yeah. In fact, I this was example in some paper mine published in the birthday volume of Leiden-Frank. I put some how to prove that in for NK, for example. You can find in that volume of birthday of Leiden-Frank.
No, but this is a sort of tradition in several mathematical circuits, just to use years, because some years are prime numbers, some just odd, some just even, or whatever.
Yeah.
So that it's actually it's as it is, right? And then, are there any more questions? Yes, let's for the moment, let me ask a question, right?
Okay.
Just because you were skipping the story of the proof. So then, could you tell what is the main idea? Just say the basic steps. Let's say a roadmap of the proof.
In fact, I can say I now I can come back now. Let me put in full screen. I don't know if can you see the slide?
Yes, I do. Yes. But I don't know what about others.
Let me tell how to get the main ideas of each one of these in a fast way, right? It's clear, for example, 4 implies 1, 2, and 3. This is clear. So let me, for example, the idea now is to prove 1 implies 3, and 2 implies 3, and 3 implies 4. The 3 implies 4, you know very well the idea. I will give the idea of 1 implies 2, and 1 implies 3, and 2 implies 3.
Yes.
So, we first prove, for example, we first prove that for each P, there is some delta, such that this intersection with the ball is locally of force 2K regular. What means this? This means that the set has half of the dimension 2K, which is always true, and we use the monotonicity formula we can use because n complex analytic set is a stable variety. So we have a monotonicity formula. So you use monotonicity formula to obtain the following CK for the following. We obtain RK and CK for some compact K in this intersection that satisfy the following. Because this is just a combination with the multiplicity and density and using the monotonicity formula. So you obtain this inequality, but in fact we obtain that X has the following property, or locally of force 2K regular. Of course, n complex analytic set with dimension K is 2K rectifiable. That is, it can be covered by up to a set of halves of 2K measure 0 by a countable number of Lipschitz image of subset of R2K. This is true because n complex analytic set has Lipschitz stratification, so you can cover by images of subsets of R2K. And now, if we assume that X is LLC homologous to K manifold, we can use the following theorem proved by Reynon and Kay. They prove it if X is LLC homologous N manifold, and which is also N rectifiable and locally all force, then the tangent cone is a homologous N manifold. But if the tangent cone is a homologous N manifold, you can use exact relative homology sequence to obtain. In fact, now you obtain the tangent cone is a homology to K manifold.
So you mean when you say that relative homology sequence, you mean the homology of Hausdorff limit sequence, that one, right?
No, now I'm using homology because the definition homology in manifold means locally the relative homology is the same of Rn. So if I put in the homology exact sequence, we obtain, for example, of the homology of the complement at 0 of 0. Of course, is the homology of the link is trivial because I know the homology of the pair CX0 minus 0 is 0 for all j between 0 up to 2k minus 1. So this is why I obtain this one. So, but this is just the hypothesis 3. So this is how to prove 1 implies 3, and how to prove 2 implies 3 is if we assume that X has no chopping cycles, we can prove the following statement. Fix it the integer R for each epsilon. There exists some capital delta and delta such that for all t less than delta, an nr dimensional cycle of diameter smaller than capital delta bounds a chain at t in xt of diameter smaller than epsilon. If you prove that, you can use the following theorem proved by Weiburd. He proved it he gave just a way to obtain that a limit of a Hausdorff limit has a trivial homology group. So you use this theorem. I don't have time to read, but if you have this Wyburn, you obtain just the item 3, just directly. So this is how to prove the 1 implies 3 and 2 implies 3, and how to prove 3 implies 4 if you have the fundamental group. Sorry, the homologic group are trivial. So if you have the link of the set is simple connected using that theorem, that if the set is a LNE, so the link of the tangent cone is also simple connected. So we obtain, for example, all the homotopy groups are trivial. So you can use now the previous result that say, so the set is LNE. So LNE plus a tangent cone linear tangent cone, you can prove, you can finish, right?
Yes.
So this is the way to prove.
Okay, then there are some
for the opportunity to explain how to prove.
From the audience, there are some other questions that, for instance, Matya Zachev was asking that if you have an explicit equation of a germ, could you give a condition if there are choking cycles?
Yeah. In fact, in the paper of I think in the paper of Lev, Ibrahim, Grandjean, Fernandez, and O'Shea, they studied weighted homogeneous surface, I think, and there,
yes.
if the two biggest weights are equal, but the third one are no, I think is the two biggest are different, right?
Yes.
I think the form is the following. You have three weights. If the two biggest are different, so that set has choking cycles. I'm right, Lev?
Yes, this is what we had actually. But it's just an example when we have the Brisker variety.
Yeah, for surface, they obtain that very nice description of to have choking cycles. I think it's a problem to have the same kind of theorem in higher dimension. Maybe.
Okay, next question from Maria Aparecida. Do you have any example satisfying the condition of your final corollary in which you have hypothesis of boundness of sectional curvature?
But yeah.
More precisely, if X has an isolated singularity, and the boundness, the boundness condition to curvature, then some other condition fits.
If you take n cone with isolated singularity, satisfy that condition. For example, this is a stupid example, but this is easy. Of course, any smooth set also satisfies that bounded hypothesis. I think has left maybe. I think only isolated singularity is not enough, because we have that Briscorn examples is we have a weighted homogeneous
I think
with isolated
example,
singularity, but that set cannot have I think that set cannot have
I think there is in
bounded.
the conical point, the curvature is unbounded in the Briscoe.
Yeah,
So that
but
it's a good question, but
it's a good
in
question.
real case, I guess I could construct an example where the curvature
Yeah.
is bounded,
Yeah.
where you have something like
She put some more
non-custodial
precise.
Mm-hmm. Yeah.
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 Yes, if you have a cone which is not smooth, for example, but with isolated singularity, um, you have a boundness of on the curvature, sectional curvature. But if you remove the hypothesis on the homotopy groups on the link, we cannot obtain smoothness, for example. Yeah, we have some examples, but in my mind now, all the examples are like cones with isolated singularity.
Any more questions?
Is it clear, Cidinha?
Yeah, she's writing nice things. There are no more questions. So let's thank the speaker that I will do it by myself, just uploading that. Unfortunately, in this YouTube system, you will not hear this thing from everybody, but it's quite good enough. Thank you for the excellent talk, Edson.
Thank you also.
So, finished, right?
I think yes. I think so.
Mhm.
Good morning, and it's a pleasure to introduce Daniel Duarte from the University of Zacatecas. He's going to speak about Nash blowups and higher blowups and prime characteristics.
Okay. Thanks, Fuensanta, for the introduction. Also, thanks to the organizers for the invitation. It is a great honor for me to be in this special anniversary of the workshop. Okay, and finally, thank you all from around the world for being here. Okay, so can we see the slides?
Yes, we can see them.
Okay, great. Okay, so this talk will be about Nash blowups and its higher order version, the higher Nash blowup, over fields of positive characteristic. Okay, this is a joint work with Luis Núñez Betancourt. Okay. So the talk is divided in two parts. Okay, in the first part, like Edson, I'm going to discuss a criterion of non-singularity of algebraic varieties, but in terms of the Nash blowup. Okay, this is the first part. In the second part, we're going to discuss some results, well, a result on the higher Nash blowup, which is like a higher order version of the Nash blowup, in the specific case of the A3 singularity. Okay. Now, these two results, these two topics are kind of different, but what they have in common is that both results were only known in characteristic 0. Okay, and I'm going to present the characteristic P version of them. Okay, so let me start by recalling the definition of the Nash blowup, which already appeared a couple of times in this workshop. Okay, so starting throughout this talk, X will denote an irreducible variety of dimension D over an algebraically closed field. Okay. Then we can define a Gauss map, okay, which sends any non-singular point, okay, to its tangent space. Okay, this one can be seen as a point in a Grassmannian. Okay, so the Nash blowup is defined as the closure of the graph of this map. Okay, we denote it as n of x. Okay, and we call it the Nash blowup of x. Okay, this is a definition given by Nash and independently by Semple. Okay, so in this Nash blowup, in the graph, we have couples of the form a non-singular point and its tangent space. Okay, so in the Nash blowup, by taking the closure, we are adding limits of sequences of these points. Okay, of these couples. So in particular, we are adding limits of tangent spaces. Okay, so in the Nash blowup, a singular point gets separated. It's separated into several points depending on all possible limits of tangent spaces. Okay, so almost by definition, the singular locus is being modified on the Nash blowup. Okay, so it is natural to ask whether this process solves the singularities. Okay, now usually when you do once the Nash blowup, if you have a singular variety, you do once the Nash blowup, it is usually singular again. Okay, so the question is whether the iteration, okay, of this process solve the singularities of x. Okay, if we continue to separate singular points using limits of tangent spaces, whether this process solve the singularities of x. Okay, this is a question that is usually attributed to John Nash, but it also appears in the work of Semple. Okay, now this question has been studied especially in the case of characteristic zero fields. Okay, in this case, there are a lot of results, okay, by a lot of people. Okay, for instance, in the poster session of the workshop, there is a poster by Nancy Chachapoyas, where she studies a related question. Okay, she gives sufficient conditions for essentially isolated determinantal singularities in order for the Nash blowup to be non-singular. Okay, this you can find this in her poster in the poster session. Okay, so this is one result. There are a lot of results in characteristic zero, but among all these results, I would like to emphasize a particular one which will be important for us later. Okay, a result in characteristic zero. Okay, the statement is that the iteration of normalized Nash blowup solves complex surfaces. Okay, so this is a variant of the original question. Instead of just taking Nash blowup, okay, here we take the composition with the Nash blowup and a normalization. Okay, so it is the iteration of this composition that solves complex surfaces. Okay, this is a result due to Mark Spivakovsky. It uses some results by Hironaka and is also partly inspired by a work of Gonzalez-Springberg. Okay, so this is a result I wanted to emphasize in characteristic zero. Now, in positive characteristic, okay, the story is quite different. Okay, to the question of whether Nash blowups solve singularities, the answer is no. Okay, Nobile gave the following counterexample. Okay, constructed the following example. Okay, consider the cusp. Okay, this plane curve, and assume that the characteristic of the field is 2. In this case, okay, Nobile proved that the Nash blowup, okay, in this case, coincides with the blowup of the Jacobian ideal. Okay, that is the ideal generated by partial derivatives. Okay, but we are in characteristic 2. Therefore, this -2 is 0, and so this equals the blowup of this principal ideal. But to blow up a principal ideal is an isomorphism. Okay, so this is terrible, because you start with the simplest irreducible curve singularity, do this Nash blowup process, okay, and you arrive to the exact same curve. Okay, so forget about solving singularities in positive characteristic in general. Okay. Okay. Now notice that, okay, in this example, we start with some singular variety, okay, do the Nash blowup, and we obtain an isomorphism. Okay, there is a well-known theorem, well-known in this area, stating that in characteristic zero, this cannot happen. Okay, if we are in characteristic zero and the Nash blowup happens to be an isomorphism, it is because the variety was already non-singular. Okay, so in other words, if we start with some singular variety, then when we do the Nash blowup, something changes. Okay, the theorem or the proof do not say whether it changes for good or for bad. It just says that something changes. Okay, of course, because of the previous example, this theorem is false in a positive characteristic. Okay, so in a recent work with Luis Núñez Betancourt, we proved that by adding some mild hypothesis to the variety, we obtain a similar statement in positive characteristic. Okay, so the theorem says, in characteristic P, prime characteristic, assume that X is normal. Okay, this is the key condition, X being normal. if we have that the Nash blowup is an isomorphism, then again, it is because X was already non-singular. Okay? So, in the rest of the first part of this talk, I'm going to discuss the main ideas, okay, that were used to prove this theorem. But first, I also want to motivate to explain how this normal condition appeared, okay, how we were motivated to introduce this condition. Of course, by the work of González-Springberg, Ilonaka, Spivakowski, we already know that normality is a good condition to introduce in the study of Nash blowups, okay? But there is more, okay? Now, the story begins with the proof of Nobile of this theorem, okay? He works in characteristic zero, an algebraically closed field, so he works directly over the complex numbers, okay? So his proof is analytical, okay? He uses tools from complex analysis, and at the end of his paper, he asks whether there is an algebraic proof of this theorem, because maybe an algebraic proof would throw some light in the original question, okay? Now, maybe motivated by this, Bernard Tessier, the following year, gave his own proof, an algebraic proof, okay? So now let me summarize, explain the main ideas in the proof by Tessier. Okay, so we have that the Nash blowup is an isomorphism, and we want to show that every local ring is regular, okay? So the first step is the following. The fact that we have an isomorphism implies that the existence of a surjective map from the module of scalar differentials of R to R to the D, okay? This isomorphism implies the existence of this surjective map, okay? Here two comments. First, this implication, okay, is a direct consequence, okay, for those who are familiar with this language. This is a direct consequence of the universal property of the Grassmannian of locally free quotients of the module of scalar differential of X. Okay, this is a direct consequence of that universal property. Now, another remark here is that this one is not an abstract isomorphism, okay? The Nash blowup comes with a projection to X, and this projection is the one that we assume that is an isomorphism, okay? So using all this, we have this implication. Okay. Now, the second step, using this map, we construct the following diagram. Okay, let me explain each arrow here. Okay, this arrow is the universal derivation from R to omega 1. Okay, this one is the previous map. Okay, the previous surjective map. Okay, and this one is any projection from R to the D to R. Okay. Now, we know that the composition of this derivation, this universal derivation, with these homomorphisms give place to this derivation of R, okay? This D is a derivation from R to R. Now, because this one is surjective, this one is surjective, this one is not surjective, but the image generates omega 1. Because of all of that, this derivation satisfies that the image, okay, of R is not contained in the maximal ideal of R, okay? So in other words, here there are units, okay, of R. So using this derivation, in characteristic zero, okay, there is a theorem by Zariski which implies that the completion of R can be decomposed as this formal power series in some element Z, or with coefficients in some subring R0, whose dimension is one less than the dimension of R. Okay, I'll say this again. Thanks to the existence of this derivation with this property, in characteristic 0 and only in characteristic 0, there is a result by Zariski that implies this isomorphism where R0 has dimension 1 less than the dimension of R. Okay? And then Tessier uses induction on the dimension, and the proof concludes. Okay? Of course, there are much more details, but these are the main ideas. Okay? Now, notice, okay, that only in the last step the characteristic was used. Okay? These two steps are free of characteristic. Okay? So, if we want to study this problem, this proof in positive characteristic, we need to avoid this last step. Okay? So, now I'm going to take Tessier's argument, okay, in another direction. Okay? Okay. Tessier's argument in another direction. Okay? Now, like in the previous slide, we start with this surjective map. Okay? This isomorphism implies the existence of this surjective map. But now, this one is a free module. Okay? So we have this surjective map, and so we can define a map in the other direction. Okay? So we can, in other words, this map splits. Okay? Because this is surjective and this is free. This implies that omega 1 can be decomposed as this direct sum. Okay? But here we already have d factors of R. Okay? This forces T to be contained in the torsion of omega 1. Okay? So now we want to study the torsion of omega 1 in this context. Why? If we can prove that this torsion is 0, okay, then this T is 0. Therefore, omega 1 is isomorphic to a free module. Okay? And a well-known criterion of regularity of commutative algebra states that if omega 1 is free, then R is regular. Okay? So if we can prove that there is no torsion, then we have that R is regular. So at this point, Luis and I looked in the literature to look for results, okay, regarding the torsion of omega 1, and then we found the following classical theorem due to Liebman independently to Suzuki. Okay, we have to restrict ourselves to complete intersections. Okay, same notation as before. Then they proved that the torsion of omega 1 being 0 is precisely equivalent to R being normal. Okay, normal. Okay, so the normality condition appears. So now notice that putting together this result and Tessier's strategy, we have that for normal complete intersections, okay, if we have an isomorphism, because of Tessier, Liebman, Suzuki, X is non-singular. And this is very nice because all of these results are free of characteristic. Okay, so this is true in arbitrary characteristic. Okay, so this is nice because our theorem was already proved for normal complete intersections more than 40 years ago by Tessier, Liebman, Suzuki. Okay, so this was like the first hint for us to introduce this normal condition. Okay, we then explored some other families, and always normality was useful. Okay, so this is how the normality condition appeared. Okay. So now let me discuss the main ideas of the in the proof. Okay, but first let me emphasize in everything I just explained. Let me emphasize two key points in these proofs. Okay, first, from Tessier proof, okay, this derivation was a key step. Okay, this derivation was a key step in his proof. So I want to emphasize it, and I want you to remember it. Okay, this capital D given by Tessier. Okay, now in the other direction, let me emphasize that we were able to conclude, thanks to the fact that omega-1 being free implies R regular. Okay, we have this regularity criterion in terms of omega-1. Okay, so please also remember this regularity criteria. Okay, so now we're ready to explain the main steps in the proof. So recall, we are in characteristic P. The new hypothesis is that X is normal. We assume that the Nash blowup is an isomorphism, and we want to prove that every local ring is regular. Okay. Now, we first look for an analogous of the CS derivation in this context. Okay. For that, we need to introduce some objects. First, we consider this set. Okay, it consists of the derivations of R such that the image of R is contained in the maximal ideal. Okay, notice the similarity with the CS derivation. Okay, these are like the bad derivations. Okay, we're looking for derivations that are not contained, whose image is not contained in maximal ideal. Okay. Okay, now in addition, we also need this second differential power of the maximal ideal. Okay, it consists of the elements in R such that all derivations send this element to the maximal ideal. Okay, this is also an auxiliary object. Now, to relate these two, we define the following map. Okay, we take the corresponding quotients. Okay, and a derivation, the class of a derivation, the class of an element, we send it to the evaluation and then take the class. Okay. Now, in a recent paper, okay, by Olger Brenner, Jack Jeffries, and Luis Núñez Betancourt, they did an extensive, very extensive study of singularities in positive characteristic using algebraic methods. Okay. In particular, okay, they introduced this function, and they proved that this is a non-degenerate bilinear form. Okay, actually, their result is much more general. Okay, they don't work only with derivations; they consider any differential operator of any order, and here they consider any differential power. Okay, so this is a very particular case for this problem. Okay, now in addition, so now we have this fact. In addition, because of the CM, we know that this isomorphism implies this decomposition. Again, because here we already have d factors, d is the dimension of R, then, again, because of their work, it is true that the dimension of this quotient is d. Okay? So, by the non-degeneracy and this dimension, we obtain that there exist some elements in the maximal ideal, some derivations of R, such that the corresponding images are units. Okay, so this can be seen as the analogous of the CS derivation in this context. Okay, of the CS capital D. Okay, in this context. Okay, so this is the first ingredient to start the proof. Okay. So let me rewrite this one. There it is. Okay. Now, the second step that I wanted you to remember was the regularity criterion in terms of omega-1. But now we are in positive characteristic. Okay. In this context, there is also a well-known regularity criterion using the ring of pith roots. Okay. This is known as Kuhn's theorem. Okay, it states that R is regular if and only if, again, the ring of pith roots, okay, of R is a free R module. Okay, so now we have the perfect analogous of what I discussed earlier in this context. Okay, so we're going to prove with these derivations that this module is free. Okay, now in this case, the expected rank is P to the D. Okay, so we introduced the following set. Okay, it consists of vectors in n to the D such that each entry is less than P. Okay, Okay, this is a set of p to the d elements. Okay, and so we can define the following homomorphism. Okay, we have this free module. Okay, so we have here as many copies of R as elements in A, and then to each canonical basis, element in the canonical basis, we associate this product x1 to the alpha 1, xd to the alpha d, where the xi's are these xi's. Okay, and then we take a pth root, and the claim is that this map is an isomorphism. Okay, and because of Kuhn's theorem, this end the proof. Okay, so these are the main ideas. This is how the proof starts. Okay, the computations are really here. Okay, the technical part of the proof is really here. Okay, actually in the proof, the inverse map is constructed using precisely these derivations. Okay. Okay, so these are the main ideas of this in the proof. Okay, of the theorem. Okay, now we know, because of Nobile's theorem and our theorem, that for normal varieties in arbitrary characteristic, if the variety is singular, then the Nash blowup modifies the variety. Okay, something changes in the Nash blowup, and so we can reconsider Nash's simple question. Okay, but now for an arbitrary characteristic. So, like Gonzalez-Springberg, Hironaka, and Spivakowski do, we may ask whether normalized Nash blowups solve singularities, this time in arbitrary characteristic. Okay, so we hope that this result will motivate the community to reconsider this question in arbitrary characteristic. Okay, so this is like an invitation. Okay, so this is the end of the first part of the talk. Okay, let's take a pause here a moment. Okay, in the second part of the talk, I'm going to explore a similar question. Okay, similar to this one. Maybe Fuensanta, are we still connected?
Yes, we are.
Yes, we are. Okay, thank you. Okay, now in the second part, I'm going to explore, as I was saying, this a similar question. Okay, but this time for the higher Nash blowup. Okay, which is like a higher order version of the Nash blowup. Okay. Okay, so let me start by, and again, of course, also in the context of positive characteristic fields. Okay, so let me start by recalling the definition of higher Nash blowups. Okay, so again, we assume that X is an irreducible variety of dimension D, and remember that the Nash blowup separates or replaces singular points with limits of tangent spaces. Okay, this higher Nash blowup is the same idea, similar idea, but instead of using tangent spaces, we're going to use infinitesimal neighborhoods of any order. Okay, so now we define for a point in X, we denote as Xn the spec of this quotient. Okay, the local ring modulo this power of the maximal idea. Okay. Okay, this is called an infinitesimal neighborhood of X of order n. Okay, and an important property here is that over the set of non-singular points, these points, these quotients, they all have the same length as OXX rings. Okay, therefore they can be seen as points in some Hilbert scheme. Okay. So we can define the following map. Okay, to any non-singular point, we associate this the corresponding point of this infinitesimal neighborhood in the Hilbert scheme of these points. Okay. Okay, and now the Nash blowup of order n is defined similarly. Okay, we take the graph, okay, of this map, and then the closure. We denote this as Nash n of x, and we call it the Nash blowup of x of order n. Okay, this is a definition given by Takehiko Yasuda. Okay, and it's also a particular case of a very general construction given by Ana Oneto and Elsa Sattini. Okay, of course, Yasuda proved that for n equal 1, this is isomorphic to the classical Nash blowup. Okay, so this is indeed a generalization of the classical Nash blowup, but this time, instead of taking tangent spaces, we use other spaces having higher order information. Okay, okay. And now Yasuda proposed the following question. Okay, is the Nash blowup of order n of x non-singular for n sufficiently large? Okay, so instead of iterating the Nash blowup of order 1, Yasuda suggests to do just once the Nash blowup, but for n sufficiently large, and expect that the resulting variety is non-singular. Okay. Okay, so now let me discuss some results on this question. Okay, Yasuda himself studied the case of curves. Okay, so Yasuda in 2006 for curves. Okay, he proved the following: in characteristic 0, the answer is yes. Okay, the Nash blowup for n sufficiently large of any curve is non-singular. Okay. Actually, what he does is to reduce the problem to formal curves. In the case of formal curves, he's actually able to explicitly describe starting at which n, all the following n's, the Nash blowup for order n is non-singular. Okay, so he can explicitly describe this n. Okay. And of course, using the semigroup of the curve. Okay, this is in characteristic 0, and as you are probably imagining, in characteristic B is false, and the same result, the same counterexample works. Okay, he proved that in characteristic 2, for the cusp, we have an isomorphism of the Nash blowup of order n with x for all n. Okay, so once again, forget about solving singularities using Nash blowups in positive characteristic in general. Okay, now once the case of curves was solved, Yasuda started working on surfaces. Okay, and he started working with the an singularity. Okay, the surface given by this equation. Okay, in k to the 3, k3. Okay, now he did some computations. Okay, and he found the following. Okay, you can do this really by hand. Okay, he showed that Nash 1 of a1 is non-singular. Okay, great. Nash 1 of a2 is singular, but Nash 2 of a2 is not singular. Okay, so of course at this point one is tempted to think that Nash n of an is going to be non-singular. Okay, but already for the a3 singularity, something very similar, different happens. Okay, Yasuda computed the Nash blowup of a3, okay, for several orders, and every time the resulting variety was singular. Okay, he found some patterns in his computations, and so he conjectured that the Nash blowup of a3 of order n is singular for all n. Okay. Several years later, this was proved, okay, by Rin Toyama in his PhD thesis from the Hiroshima University. And he proved that in characteristic 0, the Nash blowup of order n of a3 is singular for all n. Okay, so Yasuda's conjecture was true in characteristic 0. Okay, and now, okay, let's take a moment look at this theorem, okay? Luis and I, when we saw this theorem, we thought, if this result is different in characteristic P, then this would give some evidence suggesting that Nash blowup behaves well in positive characteristic. Okay, so with this hope, we started working on this problem and in positive characteristic. But unfortunately, the same theorem holds in prime characteristic. Okay, again, in collaboration with Luis Núñez Betancourt, we proved that in positive characteristic, the Nash blowup of order n is singular for all n. Okay, unfortunately. Okay, so for the rest of the talk, I want to explain again the main ideas of these results. Okay, and of course, as you can imagine, our work is strongly based in the work of Rin Toyama. Okay. Okay, so the case of zero characteristic. Okay, now to prove this theorem, the main idea is the following. First, we need to recall, okay, that the A3 singularity or the AN singularity in general is a toric variety. Okay, this is a normal toric surface. Okay, so we're going to take advantage of the toric structure in order to solve this problem. Okay, now as any normal toric variety, this one is determined by some cone. Okay, in this specific case, that cone is this one. Okay, a cone in R2 generated by these two vectors. Okay, this part. Now, as is usually the case in toric geometry, when you start with some toric variety, do some operation on it, then the resulting object usually also has a combinatorial description. Okay? In this case, for the Nash blowup, the combinatorial description, okay, in arbitrary characteristic is given by a Grosvenor fan. Okay? The Grosvenor fan of this ideal, u minus 1, ub minus 1, u3, b4 minus 1 to the m plus 1. Okay? The Grosvenor fan of this ideal. In a moment, I will recall what Grosvenor fan is. Right now, we only need to know that this Grosvenor fan is a subdivision of the cone. Okay? And this subdivision determines the Nash blowup of order n of A3. Okay? Now, what Toyama did in characteristic 0, okay, when you study this ideal in characteristic 0, what he proved, okay, he didn't compute the entire Grosvenor fan, this is too much, okay? What he did was to find one explicit cone, okay, inside the Grosvenor fan, which is non-regular for all n, okay? This means, okay, that the Nash blowup of order n is singular. Okay, this is the combinatorial analogous, okay, of being singular. Okay, so I repeat, in characteristic 0, what Toyama did was to find an explicit non-regular cone inside this Grosvenor fan. Okay, and for all n. Okay, and this is how the theorem is proved. Now, before entering the discussion in characteristic P, of course, one must ask the following question, okay? Why would it be different in characteristic P? I mean, in a lot of situations, in characteristic 0, okay, problems tend to be more friendly than in characteristic 0. So, especially in the problem of resolution of singularities, right? So, if in characteristic 0, we already have this non-regular cone, probably in characteristic P is going to be worse, right? So why would it be different in characteristic P? Okay, so let me try to answer this question. Okay, let me try to explain the motivation to study this question. Okay, and the reason or the motivation comes from the very definition or a way or how we construct Grosvenor funds. Okay, so let me recall this notion. The Grosvenor fund. Okay, for an arbitrary ideal, okay, an arbitrary ideal, and fix some vector in R to the D, okay, and consider the following set, okay. C of W consists of all W primes in RD such that the initial ideal of J with respect to this W prime coincides with the corresponding initial ideal with respect to the fixed W, okay? Now, it can be proved that this C of W for generic W is an open cone in R to the D, okay? The Grosvenor fund consists of the closure of these open cones and its faces as we vary W in R to the D, okay? So this is the Grosvenor fund, okay? A bunch of cones given in this way, okay? But I am interested in computing one specific, one of these cones, okay? So let me recall how this is done. Of course, here we need the theory of the Grosvenor basis theory, okay? Denote as G the reduced Grosvenor basis of J with respect to some order refining the partial order given by W, okay? Now, with this Grosvenor basis, with this reduced Grosvenor basis, okay, we want to, okay, we want to show the equality of this ideal, of these ideals, okay? With this Grosvenor basis, it is enough to check the equality on the elements of the Grosvenor basis, okay? So this is a typical result in Grosvenor basis theory, okay? You want to prove this equality of ideals, it is enough to check it on the elements of the Grosvenor basis, okay? And this can be actually computed, okay? You have finitely many elements, okay? And this gives place to several inequalities, okay? And this is how the cone structure appears, okay? The thing is that depending on the characteristic of the field, the resulting Grosvenor basis may be very different, okay? So suppose you start with some fixed set, okay, of generators of J, okay? In characteristic 0, okay, you do the Buchberger algorithm, and you obtain the Grosvenor basis, okay? But for the same set of generators, in characteristic P, okay, some monomials may disappear. For instance, the leading terms, okay, may disappear. And of course, Grosvenor bases depend completely on leading terms. So if the leading terms disappear, okay, the resulting Grosvenor basis is going to be completely different from the Grosvenor basis in characteristic 0. Okay, so this is important. Now, in particular, for this problem, okay, what happens? Okay, since we have less monomials, some monomials may vanish, we have less monomials, then we have less restrictions here, okay? Less monomials, less restrictions. So what this means is that if this is a cone, okay, in characteristic 0, because we have less restrictions, in characteristic P, we hope, no, it usually happens that the cone is bigger, okay? It opens. If this was the cone in characteristic 0, usually in examples, the cone in characteristic P is bigger, okay? So in the particular case of the Nash blowup, we had the hope that this problematic cone, tau n, would open in characteristic P, okay? Now we know it's not the case, but this was the motivation, okay? It was reasonable to expect a different result in characteristic P, okay? Okay, so now the proof. Okay. In characteristic 0, first. So as I said before, the goal is to explicitly compute the non-regular cone tau n for all n. This is what Oyama did. Now, as I just said, to compute a cone in this Grosvenor fund, for this specific ideal, okay, the one that I showed before, we need two things, okay? First, the Grosvenor basis, okay, of this ideal. I'm adding a 0 here just to remember, to emphasize that we are in characteristic 0 fields. Okay? Okay, once you have this reduced Grosvenor basis, you need to identify the leading term and all the other monomials, okay? Because we want to compare initial parts, okay? So you need the leading term and all of the other monomials, okay? Now, what Toyama did is the following, okay? He didn't compute the entire Grosvenor basis. This is really too much, okay, for all n. Instead, he first computed, okay, he gave an explicit description of the leading terms of this Grosvenor basis. The Grosvenor basis exists. He doesn't describe it explicitly, but he describes the leading terms, only the leading terms, okay? And this step is the combinatorially heaviest part of his proof, okay? This is half of his paper is devoted to find these leading terms, okay? Now, in principle, okay, so now we have leading terms. In principle, we need all the other monomials to find initial parts, okay? Now, in practice, we don't really need all the other monomials. Just a few are enough, okay? In the following step, and I find this really amazing in Toyama's proof, he was able to prove that in addition, okay, to the leading term, you only need an extra monomial to determine tau n, okay? So a priori, you need the leading term and all of the other monomials, okay? He was able to prove, okay, this is the second half of his paper, that you need the leading monomial and only another one, okay? And with these two monomials, okay, he's able to determine the cone tau n, okay? This is an important monomial, so let me call it Toyama's monomial, okay? Now, okay, these are the main steps in Toyama's proof, okay? So now, in positive characteristic, well, you can probably imagine the proof, okay? We have three main steps, okay? The first one, we need to prove, okay, that the Grosvenor basis, okay, in characteristic 0, the elements in this Grosvenor basis actually have coefficients integers, okay, on this monomial algebra, okay? Now, this is not immediate, this is not obvious, because in the Buchberger algorithm to compute Grosvenor basis, you iterate division algorithms, okay? So this is not immediate, okay? There are a bunch of computations to arrive to this lemma. But now, once you know this, the rest of the proof is very natural, okay? So denote as G and P, okay, the corresponding Grosvenor basis, but now in positive characteristic, okay, characteristic P. Then these two coincides when we take the reduction modulo P, okay? So if you know the Grosvenor basis in characteristic 0, take the reduction modulo P, and you obtain the corresponding basis in characteristic P. Now, we are working with reduced Grosvenor basis, okay? So in particular, the leading terms have coefficient 1, okay? Therefore, they survive the reduction. In other words, the leading terms are the same, okay? So we, thinking of Toyama's proof, he needed leading terms, okay? So now we have them, also in positive characteristic, and we want to know what about this extra monomial, this Toyama's monomial, okay? So we looked into the proof of Toyama's proof and found that the coefficient of Toyama's monomial in characteristic 0 is, and here the Nash blowup, the higher Nash blowup was very unlucky, is plus or minus 1, okay, depending on n. Therefore, when you take the reduction modulo P, this coefficient doesn't vanish, okay? Therefore, we are in the same situation as Toyama. We have leading terms, and we have this Toyama's monomial, okay? So following his argument, we conclude in the same way, okay? So again, we have that the Nash blowup of order n of A3 is singular in arbitrary characteristic for all n, okay? And these are the main ideas in the proof, okay? So just as a final comment, I would like to say that this result, is a little ironic to us, because we're trying to bring back to life the theory of Nash blowups in positive characteristic, but the first result we obtain in this direction is actually a negative one, okay? So this is a little sad, okay? But anyway, this is for the higher Nash blowup, applying once the higher Nash blowup, okay? It is probably more reasonable to iterate Nash blowups, probably of different orders, and wonders whether these solve singularities, okay? So I think that's it, and I thank you for your attention.
Thank you very much for this very pretty talk. I really enjoyed it. I think there's already one question. It says, for normal toric surfaces, the toric combinatory can be described by a special kind of continuous fractions. For the Nash blowing up of such normal toric surfaces, is there such a description?
Yes, I think so. I mean, this goes back to the work of González-Springberg. He studies, okay, in one of the first works of his works in Nash blowups. In the case of normal toric surfaces, the normalization of the Nash blowup is a subdivision of the original cone, and this subdivision, I think, is given in terms of some continuous fractions also. But you have to take the normalization, because otherwise is not true. Okay, without the normalization, the Nash blowup, even in the case of toric surfaces, is kind of chaotic. Okay, we do not have that control without normalization. Okay, so yes, this is the answer. There is a related continuous fraction construction, if I remember correctly, in the work of González-Springberg. Yes.
Another question by Xinping Sang. He says, can you say something about González-Springberg formula of Euler obstructions for higher Nash blowups?
I don't know. I mean, I don't even know if it's possible to give a definition of like a higher order Euler obstruction. I remember discussing this with Nivaldo, and I think we didn't arrive to nothing, reasonable, because the Euler obstruction is like a way to measure how vector fields, obstruction of vector fields from one variety to the Nash blowup, right? Something like that. So, and what would be the geometric, geometric situation for the higher Nash blowups? Instead of vector fields, what did you take? Okay, so I cannot say. So to answer the question, I don't know. But first question would be, what would be the definition of Euler obstructions in this case?
Another question by Ana Bravo. She says, sorry, I did not quite get it. For your first result on X isomorphic to n of X implies non-singularity. Do you need the this field to be identically closed, or any other hypothesis?
Actually, the proof requires that the field is perfect. Okay, but everybody defines Nash blowups over algebraically closed fields. So that would be the answer. Okay, so it is the real hypothesis that we need is perfect fields. Okay, and with that the proof holds. Yeah.
Okay, I have another question. So this AN, it didn't work, that you could solve it in characteristic P, but do you think there are examples where in characteristic 0 it's not solved, and then Nash blowups does solve it in characteristic P?
That would be nice. That would be nice, but no, we don't have examples. No, I think we tried directly this, in this, because it was already known that in characteristic 0 it doesn't work. So we were hoping that it works in positive characteristic, but no, we don't have.
No, in this trying with Grosvenor basis, you didn't find a way to get something that did have a non-regular cone and then it became regular, just because of the characteristic.
No, we didn't try any further examples. Actually, for A4, A5, X6, Toyama also did a lot of computations. Okay, and he was very kind. He shared them with me, and something similar happened, similar to the A3 singularity. Okay, there was always this cone, this non-regular cone for all his examples. So I think that for the AN singularity is going to be the same situation. So we have to look in other families. Yeah.
Mm-hmm. There is also Meralto Sun. She says, I guess it will be better to define generic hyperplaced sections and related first with positive divisors. It's
okay, that sounds like a statement.
And then she's asking, why not looking in DN case?
Well, this is a project. This is a question that may be considered. I mean, the thing is that DN is not a toric variety. So to give the concrete description, okay, in order to be able to compute the Nash blowup of order n, we used strongly the toric structure. Okay, so for Dn, I don't know how to begin. I mean, because to compute explicitly, like for the Nash blowup, okay, to compute explicitly the higher Nash blowup is complicated. Okay, so I don't know how to start I wouldn't know how to start in this case, but it is a question, of course.
Mm-hmm. I have another question. You said that the higher Nash blowup solves curves for a sufficiently n. Does this n can be computed from the Puiseux exponents?
Okay. So we have to be in the formal case, formal curves. Okay. So there is an associated semigroup. Okay. So what Yasuda showed is that the starting n, okay, after which all Nash blowups are non-singular, depends on the, how you call this, conductor of the semigroup, on the Frobenius number of the semigroup. So it can be described explicitly using the conductor of the semigroup. So I don't know if this conductor can be expressed in terms of Puiseux exponents, but this is the answer. Mm-hmm.
Mm-hmm. Meralto Sun says you can still use the Grosvenor fan in the DN case.
Okay. I don't know. I mean, the key ideas in the proof that for toric varieties the Nash blowup, the higher Nash blowup, is determined by the Grosvenor-Fan. Okay, there are two main ideas. Okay, first one, in the toric case. Okay, in the first one is the correspondence between orbits and faces in the cone. And the second one is the fact that there always exist flat deformations from any variety to monomial varieties. Okay, this second statement, these flat deformations, are true in general. Okay, so we will need a way to relate, these flat deformations with in the case of other varieties. Okay, without talking of orbits and all that. So I don't know, maybe these ideas of using Grosvenor fans, I learned these ideas from Yasuda, because he also uses these ideas in some papers, but he learned these ideas from some papers by Diane McLagan, Rekha Thomas, and somebody else, and they work with Grosvenor fans in a more general situation. So maybe it can be done. It will be a matter of looking at these papers. Yeah.
Mm-hmm.
Yeah.
And I guess you checked Spivakowski's proof of this normalized, that normalized Nash blowup gives a resolution of singularities for surfaces. Did you check it and see it cannot be, now that with this result it doesn't go directly to characteristic P, or?
No, I mean, to check it, I mean, the proof is very long and is very difficult in Mark's words. So we don't really, I don't really know and understand the entire proof. It's very long, but I do know some facts. Recently, Lorenzo Fantini, Charles Faber, and a third guy, I don't remember the name, I'm sorry, they proved that parts of the proof of Spivakowski's result are true in positive characteristics, okay? Like last year or something like that, okay? So some parts we already know that are true. Now, the thing is, okay, one difficult step is the following. The proof of by Mark begins with some result by Hironaka. Hironaka proved that starting with any normal surface, if you iterate normalized Nash blowups, you eventually arrive to what they call a sandwich singularity. Okay, and this result uses the same result that Tessier uses in his proof of Nobilis theorem, this Zariski result, the one that from the derivation you can obtain this decomposition of the completion of the ring, okay? And this result is only valid in characteristic 0, okay? So the first main problem is to study Hironaka's result, to look for a proof by Hironaka, to look for a proof of Hironaka's result without the hypothesis of characteristic 0, okay? And this, I don't know. This seems like difficult, okay? So this would be another difficulty, okay? But yes, it is a project. It's something that we would like to study eventually. Yeah.
Another question, Thais Dalvelo says, the toric geometry that appears in non-degenerate complete intersections can be used to study the Nash blowing up of such varieties?
I don't know. I have no idea. Maybe we can ask this question to Nancy Chachapoyas, because it seems that I don't know if the toric geometry will be useful, but to study Nash blowups of these families, I think she in the work of Nancy, she studies these determinantal singularities, and they somehow generalize these complete intersections. Here, I'm not sure. No, I'm sorry. I don't know. I don't know. But I don't think that the toric geometry will be useful in general. No, I don't think so. I don't think so. No.
Do you know how to describe the Nash blowup when it is a toric variety? No, you say. But then,
Yes.
no, you were saying that the Nash blowup, it was easier for you to do in toric varieties, no?
There is an explicit combinatorial description.
And in non-degenerate, in non-degenerate singularities, what you have is that you know you have a toric resolution. It's not exactly a toric variety, but you do have a toric resolution. So I guess this is what it means. Like, since you can describe the resolution also from the Grosvenor fan, then probably you can also...
Yes. Yes. Now I understand the question. Yes, I didn't pay attention on this non-degenerate part. Yes, of course. Yes, maybe combining what you did for Santa with Mirna and Xavier, maybe we can find some connections there. Yeah, maybe Thais, maybe. Okay.
And there's a comment here by Siriña. She says, Nancy gives sufficient conditions for the Nash blowup of determinantal singularities to be smooth.
Yes.
Something. So we wait a little bit to see if there are more comments because it takes time. There has been several comments about your cat that was jumping during the talk.
She's very excited about the talk and the Nash blowups.
So I think everyone enjoyed a lot your talk, and also this cat going around.
Okay. Yeah.
Okay. So I think we thank you a lot for this talk. It's been very nice. There are very difficult things to explain, and you have been able to make us all feel like we understand it.
Thank you.
So
thank you very much.
Now invite everyone to come to the web coffee.
Okay.
Thank you very much.
Thank you. Thank you very much for the invitation. Thank you.
Hello, everyone. We are back for this, the last talk of this morning. So I'm very glad to introduce Tamás László from Bolyai University, Cluj-Napoca, Romania. Excuse me. I'm so sorry. I'm sorry, just a second, please. There was an interference of sound for me, so I would like to just to introduce him again. So sorry. This talk, Tamás László from Bolyai University in Romania. He will speak about on the delta invariant of curves on rational surface singularities. Thank you, Tamás.
Okay, thank you, Miriam. So just let's check. Can you see the slides? See the slides?
Yes, that's
okay.
Perfect. Yeah.
Okay, great. Okay, so thank you very much. So it seems that the wheel of the online world is working, because it was not so easy to start this this talk. But anyway, so welcome everybody, and it's a great pleasure to be here and speak on the 30th anniversary of this conference, and therefore let me first thank the organizers and the scientific committee for giving me this opportunity, and second of all, I would like to wish to the organizers and basically the whole Singularity group from São Carlos health, luck, and perseverance in order to continue this series of nice conferences in the future. Okay, so as you can see from the title of my talk is about a very classical invariant of singularity theory, or the delta invariant of curves, but inside maybe a less classical framework. And why I say a less classical framework? Because however, we know a lot about plane curve singularities, but surprisingly, or at least it was a surprise for me, that we know very few things about the invariants of those curves, which can be embedded in some more wide surface singularities. Okay, so apart from the motivation and the introduction section, my talk consists of two parts. And in the first part, I would like to present you a sort of new interpretation or a formula for the delta invariant of an abstract curve. Then in the second part, I will consider curves which are embedded in rational surface singularities, and in this case, we develop a very explicit formula which can be used, for calculation in a simpler manner. So to find this very explicit formula, the bridge for us was this second part of the second topic, this new interpretation of the delta invariant for abstract curves. Here, the interpretation is much more important than the formula. Okay, so something about this project. So this project and work is jointly with José Ignacio Cogolludo Agustin and Jorge Martin Morales from the University of Zaragoza, and András Németi from the Rényi Institute of Mathematics in Budapest. And so what is the aim of the project? The aim of the project is to study curves on normal surface singularities and beyond. And the word beyond here is very prominent because the motivation for this project and the possible application of this project. So the motivation of the members of this project and the possible application of the results are very different, or were very different at the beginning. Then we tried to unify them a little bit. And so from these motivations, I would like to tell you some of them just very roughly and philosophically. So the first motivation is the topological description of analytic invariants. For example, in this case, the delta invariant of a curve. So this is a classical topic in singularity theory, and especially in the theory of normal surface singularities. And here we want to understand also not just the explicit formulas, but also the limits of this procedure. So when and how can an analytic invariant be described with the topological data? The second motivation is the low dimensional aspects. So invariance of rings in three manifolds motivated by this singularity theory. So what does it mean? This means for us that we want to get new ideas from the rich method of singularity theory and apply these ideas to the low dimensional topology and study topological invariants of knots and links in three manifolds. So those of you, maybe some of you know, so it's a good example for this is the lattice cohomology in the case of so the lattice cohomology of normal surface singularities, which gives us like a combinatorial invariant, topological invariant for the link of the normal surface singularity. So the third motivation is the semigroup theoretical aspects. So since we are going to talk about the delta invariants, so I have to say here that the calculation of the gaps of numerical semigroups, of course, numerical semigroups, I mean here the algebraic semigroups, which are realized in singularity theory. So we had, so together with András Németi, we had some steps to this direction last year, and in that work, basically we considered the Frobenius number or the conductor of the numerical semigroups, and using the singularity theoretic methods, we managed to calculate this for very interesting in the case of very interesting numerical semigroups. So the fourth motivation, it's a sort of global aspects. It will appear at some point in the talk. So it's about local contributions in global formulas regarding curves on projective algebraic normal surfaces. And the last motivation I want to share with you is it's a sort of classification problem. So we consider generic curves, so it's a minimality condition, and using the arithmetics, in some special cases, using the arithmetics of the chain classes, of some special chain classes, we can classify these objects. Okay, so what kind of results we have so far? So there is this 3 papers. The third paper is about this last motivation I told you, the classification problem, and my talk today, it will be based on the results of 1 and 2. Okay, so data invariance of abstract curves. So let's see some definitions. So what I consider an abstract reduced complex curvature, which is just a spec of a complete reduced Newtonian local ring of dimension 1. And I denote by Ci the irreducible components of the branches of the curve C. So we take the normalization of the branches, and in fact the normalization resolves the singularities. So what we get is just a smooth germ, and what the data invariant does is just measures the defect of the normality, which can be done in the following way. So it's the same as we take the integral closure of the local ring of the branch in its fraction field, and we measure the non-normality using this as the dimension of this quotient. Okay, so for example, everybody knows that the data invariant of the ordinary cusp is the dimension of this quotient. So the parametrization is given by t squared t cubed, and the dimension of this quotient then will be 1. So in the non-irreducible case, the normalization is considered as a multi-germ. So the definition will be the dimension of this quotient, which is called the data invariant of this non-irreducible abstract curve. Okay, then the question, which is an odd question, is the following. So how can the data invariant be computed or determined, at least inductively? And there are many answers for this, or many interpretations for these questions, of course. But in my talk, I would like to mention 2. The new one, which appeared in our project, and the other one, which is due to Hironaka from 1957, yes. So Hironaka's interpretation of formula is based on the Hironaka intersection multiplicity, which is the following. So I take a curve and I embed the curve in a big affine space, and assume that the curve has a decomposition into C1 prime and C2 prime, where the Ci's are not necessarily reducible, but they have no common irreducible components. So then of course I can take the ideal which defines the Ci prime in Cn, and the Hironaka intersection multiplicity, which measures the contact of these two curves, is the dimension of this quotient. So I mod out the local ring of C by the sum of the ideals. Okay, and then Hironaka proved the following formula. and the formula is that the data invariant of the original curve C can be determined as the sum of the data invariant of C1 prime plus the sum of the data invariant of C2 prime plus the Hironeka intersection multiplicity of these two subcurves. So of course we can make out of this an inductive formula. So in particular, if I take these Cj subcurves, which are just the union of the branches from j and j plus 1 up to the r, so the C has r branches here. Yes, it is here. Then the data invariant of the curve is just the sum of the data invariants of the branches plus something which measures the contacts between the corresponding subcurves, and here the corresponding subcurves are these Ci's and the corresponding Ci branch. Okay, then from this we can have some immediate consequences, since the Hironaka intersection multiplicity is at least 1, then this implies that the data invariant of a curve which has r branches is at least r minus 1. Moreover, this bound is sharp, and this is r minus 1 if and only if the curve is just analytically isomorphic with the coordinate axis of CR. This is called the ordinary tuple. Okay, so this is what I wanted to say about the Hironaka's interpretation, and then I will move to the new interpretation we found within our project. So in this new interpretation, it will be based on the Poincaré series associated with the curve C defined by Campillo, Delgado, and Gusein-Zade in 2003. So I consider the curve, and I look at the Poincaré series associated with this abstract curve. So what is this Poincaré series? So we consider the valuation Vi given by the normalization parameter on the local rings of the branches, and out of these we define the value of the functions on the curve, and this value, the value of this value, it's a lattice point in the first quadrant of ZR, and the coordinates are just the corresponding valuations associated with the branches. Okay, so using this value function, we can define the following filtration. So for any lattice point in ZR, I define the following ideas. So the FC L is the lattice point from in ZR, consists of those functions on the curve for which the value is greater or equal than this L. So we have this filtration, and for the filtration we can define the following things. So we can consider the Hilbert function, which is just the dimension of this quotient, and we can put together these Hilbert functions into a Hilbert series, which is defined by this. So the coefficients of the monomials are the Hilbert functions, and this is a this is a mistake here. So it's This is the variable here. It's a multivariable series. It should be t here. And the t to the L, so L is a lattice point in ZR, and t to the L is just the product of T1 up to the L1 times and so on, TR up to the LR. Okay, so this is the multivariable Hilbert series we associate to the filtration, and then the definition given by Campillo, Delgado, and Gussanizade around 2003 is the following. So with this formula, we can we define the Poincare series out of the Hilbert series. So this is the Poincare series associated with the curve germ C0. So the definition, of course, looks very unnatural at the first sight, but actually this is the way how we can avoid the technical difficulties coming from the absence of the grading in the multivariable case. So, for example, if we have only one variable, so the curve is irreducible, then the Poincare series is just the coefficients of the Poincare series is what you expect, is the dimension of the graded pieces. Okay, so maybe just a check if Miriam can hear me, or I'm completely alone in this. So Miriam, can you hear me?
Yes, I was muted. Sorry. Yes, that's perfect. Yes.
So everything is okay. Okay, so then I continue. Okay, so some remarks regarding this Poincare series. So the first remark is that this Poincare series defined by Campillo, Delgado, and Gussanizade, it's sort of more close to the topology in the sense of the following theorem, which is proved by them in 2003. So the theorem is about the plane curve singularities. So we consider a plane curve singularity, and we look at the link of the singularity, which is a topological link in S3. And if the plane curve is irreducible, so we have only one branch, then the Poincare series is nothing else than the Alexander polynomial of the. So here we have only one. So we have a knot. So the Alexander polynomial of the knot, and over 1 minus t. If we have more than 2 branches, then it turns out that the Poincare series becomes a polynomial, and this polynomial is the Alexander polynomial of the link with more than 2 components. Okay, so let's stay with this special example. So in the world of plane curve singularities, so C0 for me now it's a plane curve singularity, and it has R branches. Okay, then we have a well-known formula which is known by everybody, that the delta invariant it can be calculated by this inductive formula, which says the following. So the delta invariant of the curve is just the sum of the delta invariant of the branches plus the contacts of the branches can be measured by the local intersection multiplicity. Okay, now we make a little calculation here, and the calculation is as follows. So I apply the theorem of Campillo, Delgado, and Gussanizade, which I mentioned here, And I apply also the formula of Torres for the Alexander polynomial of algebraic links from 1953. And what I get is the following. So strictly in this case, so I'm in the case of the plane curve singularities. So the Poincare series of a subcurve which contains at least 3 branches evaluated at the one vector, so one, board 1 at the j means that I'm in this lattice and I consider the one vector. So if I evaluate the Poincare series, so the Poincare series by this theorem, it's a polynomial, so I can evaluate at 1, and the result is 0. If I consider a subcurve consisting of 2 branches, then the Poincare series is still a polynomial, and evaluated at 1 gives us the local intersection multiplicity. But in fact, in this case, everything matched together. So the Poincare series of 2 branches evaluated at 1 is the same as the local intersection multiplicity, and that is the same as the Hironaka intersection multiplicity. Okay. So if I put these findings into this formula, what I get is a formula, is an interpretation of this inductive formula using the Poincare series of the curve. So the contacts is measured. The contacts are measured by the Poincare series associated with subcurves with 2 branches. Okay, so of course, let me just say some remarks here. So then we can ask the question: then what happens in the case when we consider only one branch? When we consider only one branch, the Poincare series, it's a series. It's not a polynomial anymore. So I cannot evaluate it, and I cannot evaluate it 1. So I have to do something else. And this something else is what we call the periodic constant. And basically, the new interpretation generalizes this formula from the case of the plane curve singularities to any abstract curves, and moreover, extend this interpretation with the calculations, with the interpretations of a delta invariant of a branch using the periodic constant of the Poincare series. So the theorem is that we have an abstract complex curve germ, then the delta invariant of a branch is so we have here a minus sign, the periodic constant of the series, and the B part is just the generalization of the formula we had before in the case of plane curve singularities. So note that here the contacts is measured by the Poincare series. These Poincare series here are polynomials, and these are evaluated at 1. Okay, so then let's say some words about the periodic constant. So what is the periodic constant? So since the very precise definition would be a little bit technical, I would like to just describe a little bit and give 2 examples, and so just give you the flavor of what this procedure, what the periodic constant procedure does with the series. So the one variable case is defined by Okuma and Nemeth in 2009. And multivariable case is a joint work with Nemeti from 2014. And basically what I have here, I have a formal power series, a multivariable formal power series, and I have to assume some sort of finiteness conditions on the coefficients. And in the multivariable case, basically comes into the picture topological top-dimensional closed real cones, and I associate the periodic constant with a series related with respect to a top-dimensional closed real cone. Okay, so I don't want to say more about this this number. Is just what I want to say is that we associate to the series and this top-dimensional closed real cone a number. And let me give you some examples. So, for example, the special cases. If the formal power series is the generating is a one-variable series, and if it is a generating series of a numerical semigroup, then the periodic constant is here. There is a sign coming into the picture. Is the negative of the number of the gaps. Okay, so here you see immediately the connection, at least in the case of plane curve singularities with the delta invariant. If ST is a polynomial, it can be a multivariable polynomial, then the periodic constant, so here the cone can be, for example, the first quadrant of the parameter space, and here the periodic constant is just the evaluation of the series at 1. So that's why basically this last formula, this inductive formula, the periodic constant does not appear here, but behind it's basically a periodic constant procedure going on. And these are nothing else than the periodic constant of the Poincare series for the subcurves as well. Okay, so let me say something about the importance of this periodic constant. So at least how this periodic constant appeared in the theory of normal surface singularities. So, for example, if I take a normal surface singularity, then I can consider a Poincare series, also defined by Campillo, De Gando, and Hussein-Zadeh. It's based on the divisorial filtration, and if I take the periodic constant of the Poincare series, of this Poincare series associated with the surface singularity, then what I get is the geometric genius. So there exists the topological side of the story, which is the following. So I consider now the link of the normal surface singularity, which is a connected negative definite Plum tree manifold, and then I can define the so-called topological Poincare series associated with this link. And if I take the periodic constant of this series, what I get is code in the low-dimensional topology, the cyber with an invariant of the tree manifold. And now there is another. I can put another line here, so I consider an abstract curve, and I can take the Poincare series of this abstract curve as defined before, and the periodic constant of this Poincare series gives us the delta invariant of the curve. Okay, So the time, okay. So what next? Next, we want to embed our abstract curve in the normal surface singularity. Okay, and then the second part of my talk is about the data invariant of curves or rational surface singularity. So I consider now a curve in a normal surface singularity. So as before, the branches of the curve has R irreducible components, and the branches are denoted by Ci. Okay, then the question now, when and how can the data invariant be determined from the local embedded topological type of the pair? Okay, so now my curve is on the normal surface singularity, and so I assume I give some restrictions on the curve, and I would like to determine this analytic invariant somehow, the topological data. Okay, so as it is expected, in general, we cannot determine the data invariant from the embedded topological data. But for example, if we assume that the curve is a local Cartier divisor on the surface, then it seems that to be a local Cartier divisor, it's a very strong restriction. So in this case, we have a Buchweiz-Greuer formula from 1980, which expresses the data invariant in terms of the number of the branches and the mean or number of the function f, where the function gives since C0 is a local Cartier divisor, it is given by the local equation. This function. So it is expressed by the number of the branches and the mean or number, which can be determined from the embedded topological type, for example, via the Acampo formula. Okay, so let's say we want more, we want an explicit expression, and then...
Excuse me, just let me tell you that everything is okay.
Okay, thank you very much. Okay, so in order to have an explicit expression, we need the following preparations. So I would like to present you a sort of combinatorial package for the study of the topology of our ambient space, the normal surface singularity. So when I have a normal surface singularity, I can take a good resolution, and then E is the exceptional divisor, and it's the union of the EVs, and the EVs are the irreducible components. Okay, then I can consider the gamma, the dual resolution graph, and the calligraphic V for me will be the set of vertices of the resolution graph, or the set of indices for the irreducible component. And then I make an assumption, and the assumption is the following. So we assume that the link of the singularity is a rational homogeneous sphere. Okay, then Edson already touched this definition at the beginning of your morning, my afternoon. But let me just say, what does it mean combinatorially? So combinatorial means that the dual resolution graph is a tree, and all the irreducible exceptional divisors are just P1s. Okay, so what is the ingredients for this combinatorial package? So I take the second homology of the resolution space, and this will be denoted by L, big L, and this is freely generated by the classes of the irreducible exceptional divisors, And this is endowed with a non-degenerate negative definite intersection form. So I consider this lattice L. Then I can consider the second relative homology, or the second cohomology of the resolution space, and this will be the dual lattice, which is denoted by L prime, and this is generated by some dual classes, and I choose the dual classes in a way that their intersection with the irreducible divisors are the minus of the Kronecker delta. So it's not so important for us today. So then I consider the factor of L prime with L, and this is isomorphic with the first homology, first integral homology of the link, which is a finite abelian group without the free part by the assumption, by our assumption. So right. So what I wanted to say. Well, okay. So, and I denote by I consider so if I take the L prime a cycle, of course, so these are called cycles. These are the set of cycles, set of integral cycles, and if I consider a cycle from L prime, then I consider the class of L prime. It's a group element in this H. Okay, so sometimes it's very useful to take also rational cycles, and so I have the integral cycles. I have an overlattice L prime, and then I extend it to the rational cycles. I can take rational cycles, and the intersection form can be extended to the set of rational cycles as well. Okay, so then I can define I have a special cycle which is called the anticanonical cycle in L prime, which is defined by the adjunction formulae written down here. So I think everybody knows what it is. And if I have this, so I defined it purely combinatorially. So this system has a solution, and this is the anticanonical cycle. And whenever I have this anticanonical cycle, I can define the Riemann-Roch function, which is assigns to a cycle from L prime a number given by this intersection mod out by 2. So in geometrical terms, for example, these are just the Euler characteristics of some line models. Okay, so great. So apart from the anticanonical cycle, we have some special cycles which in many cases controls the topology of the normal surface singularity. And the first cycle is the Artin's fundamental cycle, or the minimal cycle. It's an integral cycle, and for example, and controls important properties of the singularities. For example, if X is rational, if and only if the chi function of this Artin's fundamental cycle is 1. So this is Artin's characterization, topological characterization of the rationality. So thanks to the work of Laufer, this cycle can be determined by the so-called Laufer algorithm. Okay, then we can generalize this cycle in the following way. So we consider the set of Antineff cycles. Antineff means that so these cycles are from the L prime, and the anti-nef means that the intersection with the exception, the irreducible exception divisors, are negative. So this is called the Lippmann cone. And then the Lippmann cone has a decomposition. So it's basically an affine monoid, but this is the name for it. So it's in the, yeah, okay. So the Lippmann cone has a decomposition according to the group elements H. So for every fixed class H, little h, I consider only those cycles whose class is exactly this fixed group element from H. So these are the sort of, it's called the Lippmann cone associated with the group element H. And then the minimal cycle can be generalized with respect to the group elements of H, and the claim is that for these sets, so this really looks like cones. So there is a unique minimal cycle of S prime H, and denoted by small s H. So you can see this is the Lippmann cone, and then somewhere here is the minimal cycle, and then for every group element H, I can determine a unique minimal cycle which is basically will be the vertex of this Lippmann cone associated with so the part of the Lippmann cone which is associated with the class, with that group element from the H. Okay, then back to the Cartier divisor case. So when I have a curve now on the normal surface singularity, I can take a good embedded resolution, and then I pull back the curve to the resolution, and then the divisor consists of two parts: the strict transform and the one supported on the exceptional divisor, and this is a cycle from R prime. So I have the strict transform and the cycle, and of course I can consider the class of the cycle in the group H, and this will be the group element associated with the curve C. Okay, if C is Cartier, then the claim is that the data invariant is the Riemann-Roch function of the negative of the cycle associated with the curve. So there are many ways to see this theorem in the case of when C is Cartier. So first, what I mentioned before is the Buchweiz-Greuer formula. We have to mix with the Acampo formula, for example, and we got the result. The second is the global theoretic point of view. So from 1995, Blocher had a theorem which saying that if I take a projective normal surface and I consider a wave divisor, then and I consider contributions are given by a map A associated with the singular points of the surface, which depends only on the local divisor class. And in addition, this map, if we consider a reduced curve germ, then this map on C is just the difference between the chi function of the minus of the cycle associated with the curve and the data invariant. Okay, so in particular, if C is a Cartier divisor, then this difference is 0. So we get back this result. Okay, so yeah, okay. So now so it's very easy to construct or let's say it's not so hard to construct examples when the data invariants really cannot be determined by the embedded topological type. But when the ambient space is rational, then in fact it can be determined. And in the followings we consider this situation. So what we want to express is this difference. What we want to find is this difference, which appears also in the generalized Riemann-Roch formula as a local contribution coming from the singular points of the surface. So if ambient space is rational, so I already gave you the topological characterization, but this means that the geometric genus is 0. So in this case, the local divisor class group is just the H, is isomorphic with that H group. Okay, and the theorem we found at the beginning of this year is the following. So I have a reduced curvature in a rational normal surface singularity. Then the data invariant of the curve can be expressed as the Riemann-Roch function of the minus the cycle associated with the curve minus the Riemann-Roch function of this unique minimal special cycle associated with the class of this cycle. Okay, so the negative of the class of the group element associated with the curve. So, for example, so if C is Cartier, of course, the associated class is 0. So at the S0, here, so at S0, maybe I forgot to tell you. So the S0, we get back the 0, not the minimal cycle. So that's why I said sort of generalization. So S0, we get back the 0. And then in the Cartier case, we get back the whole thing. Okay, so basically how we found this formula. So the main help. The main thing what helped us to find this formula was the new interpretation of the data invariant of an abstract curve, and so the way how we found this formula was completely topological, but it's not a big surprise if we found also an analytic proof. So we have two proofs. The analytic one is in the first paper, and the topological interpretation, which really shows nicely the importance of the Poincare series defined by Campillo, Delgado, and Gusainzade in this context. Okay, so thank you very much for the attention.
Thank you so much, Tamás. Thanks for your talk and for this very interesting subject. If we want to learn about the results in more detail, it would be great if you shared the papers of yourself or preprints. Actually, there are some other people interested in some other work, so we are trying to put a way to make some material available. So I'd like to invite you to share your work with us. And then we can spread it to other participants.
No problem, no problem. So no, I don't see
just one sec. I guess we have Christoph Kurtica with us, if he wants just to say hello to you.
Yes.
Okay.
Hello. So I enjoyed a lot your talk, despite the fact that it's quite far from my expertise, but still singularities of curves is fundamental, fundamental subject. And so, well, I don't know if this question makes sense, but because you started with these abstract curves, not embedded curves, and this formula for delta invariance. So they are independent of embedding, yes,
right,
somehow. But in the second part, you studied this problem for embedded curves, and to what extent, in special cases, yes, if I understand, to what extent studying these problems for on singular spaces, not necessarily surfaces, can bring us another information about the singularity of the space in which this is embedded, everything, your subject, somehow.
Yeah. So basically so of course these curves can be embedded in a big affine space as well, and there you can calculate the delta invariant, or you might try to calculate the delta invariant. So we embed into like surface singularities because so there is the idea is twofold. So first we want to study really the curves on this
yes,
singularities. So they tell you a little bit, so they can tell you more about the surface singularities as well. On the other hand, using the machinery, so in this case we use the machinery from the topological study of a surface singularities to determine the delta invariant, to determine an invariant of a curve. Of course, you can take any invariant. So this is another question. So you can take an invariant, and then you can try to get the information using a special embedding. So I don't know if you thought about this or
yeah. Yes, because in the case of surfaces, this topological embedding is non-trivial. So it contains a lot of constraints, etc. Yes.
Mm-hmm.
Okay.
Yes.
I cannot see you.
Yes, but maybe my okay. So I try.
No, but on the other hand, maybe. Well, this is also very speculative. There is this very active area of arc spaces on singular sets and this motivic integration. But everything is in the spirit of John Nash, in that you consider truncation of curves lying in, let's say, in your surface, but this truncation is because you consider parametrized curves, so it makes sense to make this truncation. But this kills a lot of. Well, this is a very brutal way to do it, and I wonder whether this approach may make sense generally for curves on surface on singular spaces, to say something about this singularities, not to truncate curves, but see them really as they are somehow. So, well, this is very speculative.
Yeah. But of course, I mean, in this case, we cannot. We don't know a lot of things. So we don't know the semigroups. So how can the semigroups are characterized, for example? So what the embedding tells us about the semigroup.
Yes.
So, for example, we calculated the Frobenius number last year, but just in the case when we have a special curve in a weighted homogeneous singularity, and the weighted homogeneous singularity does not have to be rational, for example. And here, in that case, the Frobenius number is topological, but the delta invariant is not.
Mm-hmm.
So for that, we need a strong assumption on the ambient.
Yes.
For example, the rationality.
Okay, thank you.
And there is a question from Juan Vilsos. Do this imply or suggest that the delta invariant is an invariant which can be computed using motivic integration or viral Euler integrals in a general case?
Yes, I think yes. This is just a simpler yes. I would like to see the formula if somebody can
Okay.
Can
I see another question. Sorry. I see another question. So for rational surfaces, can Weil and Cartier divisors help in the study of homology with compact support?
Yeah, I'm not sure if I understand this question. So for rational surface singularities or homology with compact support of what? So
Oh, that's no problem. So that's okay. We can.
Yeah, I don't really understand the question.
We can clarify afterwards.
Yeah. Okay.
Right. So I think that's it. I want to thank you again. Sorry for the problem in the beginning. Thank you very much for participating in this conference, Tamás. Thank you.
My pleasure to be here. Thank you very much.
Okay.
Hello, everyone. That's very good that you are sticking with us in this very special week for the singularists. It's my pleasure to introduce the afternoon parallel talks. At 2 p.m., we have Ingrid Sofia Mesa Sarmiento from Federal University of São Carlos, Brazil, and also Thiago da Silva from Federal University of Espírito Santo. At 2:45 p.m., we have Philippe Belle da Nóbrega from École Normale Supérieure de Lyon, France, and also Maria Michalska from Federal University of Ceará. And we have a break at 3:25 p.m. And then at 4 o'clock, we have Cassiano Oliveira Souza from Federal University of Uberlândia, and also Piotr Murmu from University of Warsaw from Poland. So you have here the links to visit their talks, and I would also like to introduce or to announce the SIMPA School, which will be held next year here in São Carlos from July 12 to 23. And all information you can find at simpa.icmc.usp.br. So thank you very much to being with us, and see you tomorrow.